Hi, in this video we now move to the topic of introduction to statistics with R. And the first thing what we look at is the probability distribution functions, that is a density function, distribution function and quantile function for the different distributions. In R they are usually for mostly used distribution, they are available these sort of functions which can be used. For example, in case of normal distribution we have this sort of a function as d norm for density function, p norm for distribution function, and q norm as a quantile function. And if we change from one function to other, then the idea is that there's still this same sort of a density function, distribution function and quantile function. And so, for example, in Poisson distribution case, these functions are named like this. And the basic R already has quite a lot of these sort of functions for different distributions. And if you need some more rare distributions, then I'm sure that you can find quite easily a package which includes those sort of basic density distribution and quantile functions for that considered distribution. So let us first start with these examples given here. So obviously the normal distribution is the most often used distribution in statistics, in a case of responsive variable being the quantitative in nature. So it is obviously quite important to understand how to do calculation, how to do probability statements, how to calculate probabilities in a case of normal distribution. So if we want to calculate some probability, for example, that some random variable y, which is following the normal distribution like this, is having a values bigger than 10, then we can use really this sort of a p norm function, which is calculating us to the distribution function, cumulative values for cumulative distribution function. And in this case, when we put here the lower tail false, it actually calculates these sort of probabilities. In a case of expected value, that is a population mean being 5 and a population standard deviation being 2. So when we are using the normal distribution functions, we are giving them this sort of a variation is given by this sort of a standard deviation notation, or the value, what is the value of standard deviation. And when we then give or define mathematically what sort of a function or what sort of a distribution we are considering, then we are giving it as in a variance form. So here this value 2 is always square root of this value. So if we change, for example, here the distribution to 5 and 6, then we should take here actually the square root of 6 in place of this 2. Anyway, so so we will get this sort of a probability for calculating this sort of a result for this probability when the y is distributed like this, which is obviously quite small. Then there's a quantile function q norm, which gives us the value of this little y, which is for which it holds that cumulative probability distribution for y being small or equal to this random variable y being smaller than equal to this little value y being equal to 0.95 when we still considering the same normal distribution, then this sort of a value is 8.289 and so on. And it's obviously useful to sometimes plot these sort of functions how the distribution is looking like, and it's usually best to plot by using the density function. So here is actually we use the function plot, which is used for plotting. That is something that we look next time more carefully when we are considering the graphics in R. And then we have here this sort of a function going on, and this is what we could call as a functional programming. And this is our last topic, how to create our own function in R. But in the end, we use here this d norm, density norm. So we are for normal distribution. So basically, we are calculating the values for density function in normal distribution, mean 5 and variance 4. All the values from -2 to 12, and then we plot it. So if we go for R, we can do the same things here. So if we go to this R, we can now do here the same thing. So here is this function of p norm, how to use that. So this gives us this sort of a probability. If I now calculate, if I take here the log of, or if I take this out like that, this is by the way square root of 2 4 is same as obviously the square root of 4 is obviously same as the square root of so the square root of 4 is obviously equal to what? 2, like that. So I could put it in this way. So but if we take this away, this lower tail is false, we actually take calculating probability of y being less than equal to 10. So that probability is obviously like this, and this is like 1 minus probability of given here. So we were now calculated the complement events here basically, so that's why it holds like this. So that's pretty much when you want to calculate these sort of probability statements. For example, if you want to calculate the probability that y is between 10 and 10 and let's just say 6, then we could use it in this way, so that we calculate probability that y is equal to or less than equal to 10 minus probability that y is equal or less than 6. So this gives us the probability that y would end up being some value between 6 and 10, and that would be like something like 30%. So the next we have this Q norm, which basically is giving us the quantiles. We can obviously calculate these quantiles for many quantiles. For example, if we have this sort of a distribution and we find out, for example, sequence of quantiles from 0.5 to, let's just say, 0 to 0.99 by 0.1. So we calculate all the possible quantiles from 50% to 99% here. Then the values are like given here. Oh, sorry, we should have put it more here, the decimals. So this is for each, after each percent. So obviously 50% quantile is actually the mean value, and after that we get these sort of quantiles, and 95% quantile is the value like here. So that's a quantile. We always need that sometimes when we are calculating some things, it is useful function in many cases. So the third thing about is this plotting the density function. Here I've used this sort of a plot function, which is total of giving us the graphical way how the distribution is behaving. Obviously we could calculate here, for example, if we start changing the parameters a little bit. for example, if we change the parameter from 4 to, for example, the population mean to 2 to 8, then the plot would look like this way. And on the other hand, if we change from let's just say that we have a population mean 5, but let's just say standard deviation is like 5. Then we have, we should have plot other way around, so that is add 2, 5. We should start it again like this way. I should start again. So this was the original plot. This is when we have much wider variance, then the plot looks like this way. And if we just put it also that case when we have a population mean different, it looks like this way. So changing the parameter values, and that is the expected value and the standard deviation, you can then see how this normal distribution is behaving. So we can go to the next questions, which are like if we do the same things for Poisson distribution. Poisson distribution is the distribution used in a case that a random variable y can have integer values, that is values like 0, 1, 2, 3, 4, and so on. So, for example, if we have a lambda set in a Poisson distribution equal to 5, it means that the population mean is 5. So, if we calculate now the probability that that Poisson distribution with the parameter lambda being equal to 5, the probability that y has a values let's just say this should be like this, less than equal to 1. Then we have this sort of a way. So we have a typo there. I have to correct that. So it's this way around. And for quantiles, if we want to calculate the quantiles in a case of Poisson distribution, lambda being 5, then we can use this sort of a function, and it gives us the value 9. It actually then tries to find out the best, the closest integer which is filling this sort of a probability, like here, or the smallest one which fills this probability at least. And if you want to plot this sort of a discrete type of a function, discrete type of probability distributions, then I guess the best way is just to calculate the density, that is a probability mass functions values for different values which this density function can have. For example, here I have calculated in a values from 0 to 12 all the integer values, that means 0, 1, 2, 3, so on, the value of the density function in the case of Poisson distribution being parameter lambda being 5. That's why we get this sort of a probability density function values. And if I now use the plot function again, I can plot it in this way. So, for example, now the mean, population mean is actually this lambda value 5. That's really what the lambda means in Poisson distribution. So, for example, if I change this from 5 to 10, then I have to same time calculate with different values, because otherwise we are missing a lot. So I calculate the values from 10 to 12, and then if we plot the function, how the probability density function or probability mass probability function is looking like in this sort of a case, it looks like this. So Poisson distribution is sometimes called as a normal distribution for integer values. And so it starts to be like this sort of a symmetric when we are having when the lambda is something clearly something else than something else than close to 0. And of course it cannot be 0, because then the probability, it's just then only values that are available for Poisson distribution are zeros actually. But you can just simply change the value of lambda and see what sort of effect it has on the distribution and for these graphs. So if we continue with this distribution, then closely related for this distribution is this sort of a random number generation, and closely to the random number generation is the sample function. I should now mention that I just took this normal distribution and Poisson distribution as an example in these slides. There are a lot of different distribution in statistics, and for each of these distribution you can pretty much, I'm sure you can find at least, if not it's already in a base R, then you can find really this sort of a package where you can find how to use those sort of a distribution which you may need in your research or studies or in a workplace. Anyway, so when we're talking about random number generation, then we mean that we are artificially generating some sort of a realization from some distribution. And for R, we are, for example, in case of normal distribution, the function is R norm, and for Poisson case, this random number generation, we can use this sort of a function called R poise as a way of simulating the values from Poisson distribution. And then there's this sort of a sample function, which is a bit more specific, because it takes some sort of a subsets or samples from specific size from the elements it has been given to it, and we can give even the probabilities how these samples are taken from this set of elements. And if we first consider this R norm function, which is now way to generate, for example, 1,000 observations from this normal distribution 5,4, then we can just use it like this. So there's a function R norm, 1,000, mean 5, standard deviation 2, and then we can then see we have then in a vector y we have a 1,000 observations, which are like a realization from this distribution. And if we calculate, we can calculate or draw the graph of how they are distributed by using, for example, this sort of a function hist, which is drawing us this sort of a histogram. But if we calculate the sample mean of these 1,000 observations, then they are pretty much close what is said here, and standard deviation, sample standard deviation and sample mean, they are pretty much close what we have defined here as a population mean and population standard deviation. And same thing really applies to the Poisson distribution. We can here also to use this R plus function, and in case of that we get values, integer values, and then if we want to plot how they are distributed, we basically have to do some sort of a first tabulation, that is to calculate the frequency or how many times each value has occurred, and then use the bar plot for that tabulation to draw this sort of a bar graph where we can see how many values was in this vector y after this generation of random numbers. And if we calculate the mean and standard deviation in a case of Poisson distribution, we get mean, sample mean close to 5, which is really the value lambda, and then we can actually calculate the variance, that is the standard deviation raised to the power 2, and it should be also quite close to this lambda 5. And then we can look at this sample function, which is basically taking some set of values here, for example, numbers from 1 to 100, and here I have asked it to sample integer value from 1 to 100 100 times, and each time one number is drawn here, each number has really equal opportunity to be picked up. It is replaced so that next time it could be actually taken again. And this is basically generating the numbers from uniform distribution, discrete uniform distribution with lower bound being 1 and upper bound 100. And then we can use this sort of a table to get a frequency table for each of these, how many times each of these possible outcomes has occurred. That is the frequency table, and then use again the bar plot to draw the graph of that table. And more complicated case is that we use the sample is that, for example, we have a numbers from 1 to 5, and we want to generate numbers from 1 to 5 times, the 100 times. Each time each of these numbers can occur, so that we have this sort of a argument replace true. But let's just say that we pick number 1 with the probability of 0.05, number 2 with the probability 0.1, number 3 probability 0.45, and 4th with the probability 0.25, and last possible outcome, that is the 5 with the probability of 0.15. So rather than giving each of these elements equal chance to occur in our random vector y as a realization, then they can be picked up based on these probabilities. And again, then we can draw for example, the end result after doing this sort of a sample. Each time we run the sample, we get a different result. And a table would look like this, and then we can obviously do also bar plot in that case. So if we now go to the R here and do the same things here, then we can see that, for example, if we generate now the random numbers from normal distribution, we get this sort of a result. That means that we, first of all, we have here now 1000 numbers from this distribution. Then we can, if we draw the graph, histogram, it looks like this. So these values are, if you draw the histogram, looking like this, so they are looking like what in a normal distribution case they should be looking at. And if we calculate the sample mean, we get this value is very close. What is the underlying the distribution where these values has been drawn? So the sample mean is very close to the population mean, and standard deviation is also what is there as said when we define the normal distribution where all the realization were generated. And if we calculate the variance, it then should be like 4, very close to 4. And of course, the more we do that, it depends on how much we have a computing power. For example, this was a ton. If we take 10,000, then calculate the variance and mean, we start to get closer and closer. And if we take not just 10,000, but let's just say 100,000 observation, if we draw the histogram of these things, they looks like this. So we have here now 100,000 observation here from this distribution. So very quickly and easily. So that's it. And the same thing applies to the Poisson distribution. But now you have to understand, if you run with the Poisson distribution with the lambda 5, the values are like this. So they are integers. Possible values are 0, 1, 2, 3, 4, and so on and so on. And if we use the word a table y, then we can see which values have occurred in our vector y and what are the frequencies, how many times these values have occurred. And if we then do this sort of a bar plot, then by using this table, then we get this sort of a kind of graph here. So it just tells us how the frequency of, so it's basically plots this table. So on here on the x-axis is the possible outcomes, and here the side of the bar is always the relative frequency or the size of this frequency given in this second line. And so that's generation of our random variables from Poisson and normal distribution. And if you have some other distribution in mind, I'm sure you can find this sort of a R, whatever the name is, the distribution function, so that you can generate the random variables from that distribution. Then we have our sample function, which is given here, so that a sample function can be used to pick up some elements sometimes, maybe with replacement being true. So for example, in this case, I try to pick up many times, actually 100,000 times, the values from 1 to 100. And here are really the table how it looks like. So here are really the numbers which has occurred. So here this is now again integers, but now only the values from 1 to 100 can occur. And since I picked up them many times, then the table, that is the frequency or each number, how many times it has occurred in this after using this sample function, it looks then as a bar plot like this. So this could actually be said that this is a generation of random numbers or numbers from 1 to 100 from uniform distribution, discrete uniform distribution. But you can use this sample function, but so much easier you also. So for example, if you have a, let's just say that we have a sample and we have a character vector, for example, A, B, this could be just names for, I don't know, some products or whatever, and D and E, for example. Then, for example, if we put here like we should generate the values from this list 10 times with replace true, then if I run this code, we get this times this sort of amount of this sort of outcome vector. If I run it again, I get a different kind of, and so on. So this is the way how this sample function is working. And if I say that replace is false, then it actually does not work here, because there's less elements than is needed to picked up, so it cannot function. But if we have picking up two elements from this list, the first one is this E has been picked up simply randomly selecting one of these elements, and after E has been selected, then the B was then selected based on randomly selecting one element from this list. So the replace false is working in like that way. And for us, what is the interesting thing is that if we have, for example, values like 1 to 5, which could be denoting like the opinions in some surveys for some questions, and we have let's just say that we want to generate this sort of a sample size of 100 values from 1 to 5 100 times, and replace is true, so that each of these values can occur multiple times, this 1 to 5 integer values, but we can give them probabilities, how often they are occurring, and that is really what we have done here. So if I now do this sort of a line, so the probabilities are given here, prop and equal. So you should be noted that these probabilities, they must sum up to the 1. so that if we have like a 5 different, so for each elements which are there to be sampled, I give a specific probability like this way. So this probability is related to the value 1. This probability is related to the value 2. This is for value 3. This is for 4, and this is last one is for value 5. And if we now look at the table after 100 sampling 100 times with these sort of probabilities, we get these sort of frequencies. So they are not anymore equally distributed or uniformly distributed. There is more value 3 occurring in this random sample, since we have given that sort of a weight when this R function is generating these numbers. So that's of course interesting and good to understand. And then the bar plot would show us how our generated data vector is, what are the frequencies for that vector. After the probability distributions and random number generations, let us now continue to the contingency tables and relative frequencies. Well, the contingency tables are also called as a crosstabs, which might be a more familiar name for you. And we are using this sort of a table especially in a situation where the response variable y has, let us say, few qualitative values, and also maybe the explanatory variables have only few qualitative values. And in that sort of cases, we like to make those sort of crosstabs or the contingency tables, calculate these sort of conditional relative frequencies, and then make inference based on those conditional relative frequencies, which are kind of estimating the probabilities of y getting to certain value given that x explanatory variable is set on some level of or some value. So what we really need here is this table function, which is constructing us this sort of frequencies. That is it gives us the frequency tables, and in case of we have 2 variables, it gives us the 2 frequency tables for these 2 variables. Same applies to the x steps, but it's bit more, let's just say this way, that we can here use this sort of a formula interface to come up with these tables. And then there's an important thing which is PropTab table function, which creates us this conditional relative frequency which we need to make our inference. And then there's a chi-square test kind of function which performs the chi-square test for this contingency table, pretty much test the hypothesis that is these sort of conditional relative frequencies equal to the different categories of x variable. That is, we calculate these sort of conditional relative frequencies for given the value of x to the values of response variable y. So if we go now to the R and see these examples or these codes there, then we go here, and so let me first use the sample function to create this sort of artificial data. So every time this data comes different if you run it again and again, so you cannot really have it same form. But I think the idea here is that we have a x variable which can have 3 different values called a, b, and c. And for each of these categories defined by this explanatory variable a, we have now values related to the y variable, which can have values 1 to 5. So this could be like a some sort of a survey we asked with the 5 categories of strongly disagree to all the way to the strongly agree some statements or ideas. But this case, I'm creating this sort of artificial data in a way that in the case of subpopulation A, that is subpopulation defined by this x variable, we think that these values 1 to 5 are coming with these probabilities. They are realizing with these kind of probabilities. Of course, in the data, when we make this sort of a 87 realization from this distribution, then obviously the values we get for YA vector are not exactly these sort of probabilities, but our relative frequencies then kind of estimates these true probabilities. And same applies to the sample or the population B and the sample YB, and then we have YC. So if I'm running this code, it means that we have here now these vectors YA, which looks like this way. So there's values from 1 to 5 with these sort of probabilities, and you can see that there's not so many ones because the probability of one occurring is just 5%. And same applies to the B and YC. So we can make this sort of Y vector which just contains all these 3 vectors and or join them to one vector Y, and if we then also create this sort of a X vector which just tells us which was the population in a case of subpopulation in a case of observed value Y was obtained. So we now obviously think that first we know, or we set even ourselves this subpopulation or this value of X, and on the condition that this is set, then we assume that Y is having its value. So what we can now use this table is to make this sort of in this case, because this is a this has a Y variable has 5 categories and X variable has 3 categories. We could call this as a 5 times 3 frequency table. We could also call it as a 3 times 5 frequency table. But I use usually this sort of a way of doing this sort of crosstabs, that I kind of want to have my Y variable and its values in as a row variable, rows denoting the rows, and the subpopulation defined by the X variable are set on the columns. This is not a universal way of doing it. It can be either way around, but just for sake of keeping things some sense similar from time to time, this is really what is happening here. So we have, in a case of subpopulation A, we have here like a 3 times. So that means that in this vector YA we have 3 times 1 occurring. That's why in a frequency table or this contingency table created by this table it gives us this sort of frequencies in a subpopulation A, like 3, 10, 40, 25, and 9. And in subpopulation the subpopulation defined by the explanatory variable in a category B, we have the frequencies like that and that. Since the sample size is different from each of these tables or each of these subpopulations, these frequencies are not immediately. You cannot just make an inference based on these frequencies itself. But the idea is to consider what sort of a conditional, given that we have, for example, in a subpopulation A, what is the probability that y get a value 1, y get a value 2, 3, 4, and 5. We obviously know the true probabilities which are set here. But in real life, we have this sort of a frequency table, crosstab, and based on these frequencies, we should then be able to estimate what are these probabilities. And for that, we use these frequencies, relative frequencies, conditional relative frequencies, which we can obtain by using this prop table function. So first, in that prop table function, we create our table, and then we define on which direction these conditional relative frequencies are calculated. And because I've set my explanatory variable x here as a column variable, like here, that's why we calculate these conditional relative frequencies with the margin, with respect to the margin 2. So if we now calculate these things, we get this sort of a thing. And now for each of these columns, these are relative frequencies. They sum up to the 1, and they are our estimates for these true probabilities. So based on this data set, for example, we estimate that we know that this is a true probability because we have generated the data from these sort of probabilities, but this is our estimate. If we only had the data and we needed to kind of think that what is the probability given that we are in a subpopulation I for y to get a value 1. So that's like almost 3.5%, and so on. And now the idea why we are doing these sort of cross tables, because in a true life we really want to know, does the probability of is the probability distribution of y or conditional probability distribution of y, is it the same in different categories of explanatory variable? And since we can see already that they are not similar, because here, for example, people have given a more, based on these conditional relative frequencies, we would estimate that the probability that in a subpopulation B they are y is getting values like 1 and 2, much higher probability than in the case of subpopulation A. So there's a strong suggestion based on this descriptive statistics already that it seems like from changing from population to another, these probabilities, these conditional probabilities for y getting some value are changing, and that we would interpret it as that x has an effect on the probabilities for y values occurring. And for that, the real idea is that if we use the chi-square test, it really is just doing statistical test. Is these conditional probabilities, these conditional estimates for conditional probabilities, which these conditional relative frequencies are they equal? Can we assume that underlying where these relative frequencies have occurred, are they in the underlying these true probabilities similar in each of these categories defined by x variable. And since our estimates for these probabilities shows that there's a strong belief that they are not same, we obviously know ourselves that they are not same, but in true life we don't know the true probabilities. We just know that we just have this data, and based on that we made estimates, and we have to make a test, or maybe we want to make a test that is this based on these relative frequencies which we have calculated. Can we make a inference that also the true probabilities differs, or are they same? And our hypothesis is that they are same from when we are changing from column to column, and the alternative hypothesis is yes, the conditional distribution is changing in some sense when we change from subpopulation A to B, or to A to C, or B to C. And now here we get this sort of a chi-square test where the test statistics is this one. We are not going to the details how this is calculated. That belongs to the basic statistic course. And then we get a p-value like here. So if you, for some reason you need to get a test statistics, then you could use this sort of a word like that. And that's really returning your test statistics. And the p-value can be just get by, is it a p-value? No, p-value. Yes, by this way. So by the way, if I'm writing, like for example here, that this is some object A, then using this sort of function like str an object, you can get you know more about how to get different things. So statistics is get by using this sort of a command. P-values get by using this sort of a command, and all sort of things can be get out. For example, if I put here the expected, then this gives pretty much what sort of frequencies we should have seen if the conditional distribution were actually same from categories, that is conditional distribution of y is the same in the different categories of x. So and since because our observed values are different. By the way, we can now actually calculate pretty easily this what is happening. So if we take the 1a minus a expected values. Sorry, we cannot properly do that because it does not give us the it cannot make the, we should make this as a matrices and then try it again. So okay, let's not try to do that. But anyway, that's how the chi-square test is basically coming up. So it is by comparing the sorry, I was really doing the wrong thing here. We need to put this table. Let's just call this as a table now. So if I take the table minus a expected, which was this a was given by this. So this is a difference. If we now raise these differences to the power 2 and then divide them by expected values again with the elements like this way, and then if we sum everything which was done here, we get the chi-square statistics. So that's the chi-square statistics, how it's calculated basically every time we have this sort of a frequency table based on two variables. So so that's it. So but then there was another thing here, what is called by this function xtabs, which is the way of another way of forming this sort of crosstabs, is that in this case we need to use this sort of it gives us the formula type of way of defining the contiguity table, but from which strangely you start with usually with this sign, and then you tell the variable. So in putting them in a between them putting a plus sign. So this gives us the similar kind of table. And if you put it the other way around, it just changes the row and columns. You could make the same table in this way too. Also, it doesn't really, the invariance itself does not change at all. It's just that, for example, if I call that now as a S table, then the chi-square test for this S table gives us exactly the same test statistics and p-values and so on. This just it happens to be that way. But yeah, and one thing is that if you have this sort of a whatever way you have created your table, for example, if you have a D table, you can call this sort of a margin table. Margin table for T, and you need to give a margin there, like sorry, I'm getting confused here. There needs to be margin table. Okay, it calculates everything, but if we put here the margin, for example, is 2, then it calculates the frequencies in total frequencies in these categories of x. So obviously, if we take the T and divide it by just this margin table, we could get, depending on how the R starts to run it. Okay, it does not run it in any ways. In some sense, we could have get these sort of relative frequencies in this way. So in way, relative frequencies calculated, conditional relative frequencies calculated just that we calculate the margin, that is the total sample size in that subpopulation, and then the frequency of different categories are divided by this total sample size in that subpopulation. So this pretty much covers the cross tabulation, and this is important stuff in a sense that if we have if you think about the introduction to statistics, if we have if our response variable is having the let's just say it is a discrete or qualitative in nature, our response variable, or if it just has, for example, 5 or 6 different categories of values, and then we usually somehow use these sort of crosstabs to come up with the idea of how the x is affecting the values of y, or the probabilities of y occurring in a certain category, and then the classically chi-square test is the sort of a statistical test to verify if there's a really statistically significant differences in these conditional probabilities based on these sort of observed conditional relative frequencies. Now, after we have learned something about frequency tables and cross tabulation, let us now consider this sort of example 2.1, where we should consider this sort of a data file called retinopathy, where we have some more than 600 observations of persons who have been diagnosed of having diabetes, and now they are kind of classified if they have this sort of a eye-related illness called retinopathy or not. And so this is our Y responsive variable, where there's 3 options: no retinopathy, this kind, and the last one, third, or what is coded as a second option, is that advanced retinopathy or blindness. And then we have this sort of explanatory variables as smoking or non-smoking, does the person smokes or not. Then we have how long person has been diagnosed of having diabetes, and then other things given here. And we should now create a contingency table, that is a cross tabulation between variables x1, which is this of telling us if the person is smoking or not, and this y variable retinopathy, and we should create also the crosstab which contains the conditional relative frequencies of different categories of y variable in different categories of variable x1. And after we have accomplished that, we should use these conditional relative frequencies to estimate these sort of probabilities. That is, if the person is a smoker, what is the probability that she or he has still on. Of course, we have to understand this is related to the population of persons who have been diagnosed as having diabetes. And so in that population, if the person is also smoking, what's the probability that he or she has not been diagnosed of having an advanced level retinopathy or blindness? So these are like this y of being equal to 1 or smaller means that y can have values 0 and or 1. And then we should perform the chi-square test for contingency table between these two variables. And the last question is completely different kind of, and we can get that once we have solved this first A, B, and C. So let us do the cross tabulation here now. So if we go to this example, then just using this sort of a table, ret SM, we need to first create, of course, read this data before we continue. So the data looks like this way. So here, like this way, and table which is asked to do here is basically frequency table. It looks like this. So if we are in a case of non-smokers and smokers are here, and if you look these sort of frequencies, I don't think there's really a severe difference. It may be a little bit. I guess the 1 was obviously should have gone on smoker. 1 is a smoker and 0 is a non-smoker. So that makes sense. But I'm not so sure I'm not so sure is there any big difference. Anyway, so that was the frequency table, and if we take if we want to calculate the conditional relative frequencies, then we use this prop table function, and we get in this case these sort of probabilities. And if you look these categories, so given that, oh sorry, that's not right, we need to have a margin given here. So the margin should be like 2, so that otherwise it doesn't make any sense. Or it just calculates the total frequency, so considering these two as this both of these variables as a random variable. But we do not consider that. We just think that first happens this x is set, or it is has happened to have a certain value, and then we see on condition that we are on some subcategory of, or the category of x, what sort of a values y is getting with which frequency. And if we look these conditional relative frequencies in case of so comparing, basically treat the category of 0, that is non-smokers, and category of 1, that is smokers, we can see that there's obviously some amount of change. For example, this is 66% of persons who are not smoking are kind of classified to the not having any severe problems with the eyes related to this retinopathy, and in the case of smokers it is even smaller. Well, if it's smaller, then it has to be higher in some categories, and it's especially higher in this category compared to this one. But then again, if we go to the severe retinopathy, then it goes really another way around, these conditional relative frequencies. So this really gives us an indication that it's very hard to, or the differences does not seem so clearly different that it would make it's hard to go and say that yes, smoking is affecting highly to the probability of person in a population of diabetes that person will have also retinopathy. So that's pretty much our question A. We should have now returned, for example, this one as a value, but I had a code clear mistake, because this really needs to be here, otherwise this doesn't make any sense. So what is said about the next time? So next question was that we should use conditional frequencies to estimate the probability of y being small or equal to 1, given that person is a smoker. So in this notion, this y means that this is happening, the retinopathy is happening to some person who has been classified, who is a smoker. Then we want to know in what probability that person would get in this related to this eye illness, that he or she would get this sort of a classification of being either completely healthy or no, at least advanced retinopathy. So we get the estimates for this probability by simply going here for these relative frequencies, going into this category of 1, that is the smokers, and see what's the probability of person getting value 0, what's the person probability of in this subpopulation getting to value 1 with respect to this retinopathy variable. And if we sum these two numbers, they are telling us that what is the probability of a person who is smoking is getting a y variable as a value 0, 1. And that's why if I sum up these first two rows in a second column, then we get our probability, and it's given here. So 84% of person who are smoking are not really having are not suffering from severe retinopathy or blindness. So in question C we were asked to do the chi-square test, and we can do that. We take this table, do the chi-square test, we see that test statistics is getting this sort of a value, and a p-value is like this. Well, because the p-value is so small, I guess we should make an inference that yes, smoking is affecting the probabilities of retinopathy. But if you look where the difference really comes, it comes really here. So there is a tendency maybe for smokers from not being anymore in a category of 0 but moving in the category of 1. But on the other hand, this relative frequency of this category 2 is not really increasing, or quite opposite actually, that when we are moving from this subpopulation of no smokers to smokers. So that means that there's also some flawness in chi-square test statistics, in a sense that if the sample size gets a bit higher, quite small changes or small differences in conditional relative frequencies will then turn into the chi-square test statistics, showing that there is a statistically significant the true conditional probabilities which are underneath there, they are statistically significantly different from categories of X. So we have now performed this contingency table here for these variables, and we should now consider this sort of what is the difference between expected value of the variable y in the categories of X, and create a confidence interval. So we mean that if we have a categories defined by this X variable, then there's this subpopulation 0 and subpopulation 1, and we may be interested of considering it. What if we take these values as just numbers, and if we look the conditional relative frequencies, and based on that we calculate this sort of a mean value for these numbers, and then we could do that if we did it in a subpopulation 1, we could do that in a subpopulation 0 too, and in that way we would get might be an interest also to consider what are these expected values. So maybe we should have here exactly mu0 and mu1, so that they are related to the categories of smoker. And and because here we have I guess the right sort of a notation. So here the subscripts are bit bad, or they are complete, you could say that they should be corrected in a way like, as given here. So we can now, even though our numbers for y variables are clearly some sort of a codes for these categories, there's still possibility that we calculate the sample mean and use that sample means or conditional sample means as a way of estimating the expected value of mu0 and mu1. And then we could start considering this sort of a prediction interval, the confidence interval for the difference of these expected values. So so if we use, for example, this data set, and if we do it this way, that we, for example, to calculate by the apply function, and we take this red, and if we take SM, like here, fun is a mean, then we should get these sort of values for sample means, conditional sample means in these two categories. And now really the difference is, if we want to calculate, so these are the estimates for the mu 0 and this is estimate for mu 1. And the confidence interval for this case can be obtained by again doing this sort of a t-test statistics, which is given here. And then here we have this sort of a confidence interval also, which is kind of test is the difference equal to 0, it calculates this sort of a confidence interval for the difference, and if this confidence interval includes, for example, the value 0, then it means that in that risk level the null hypothesis holds. So this was our estimates. We were able to now to calculate by ourselves, and then the difference is then between these numbers. So we can use that as a means of calculating the difference of sample means. So it's, I think in my opinion, they are pretty close. And then what is asked here to do is to calculate this sort of a confidence interval for this difference. Now, if we kind of forget about that this is not really a situation where the normal distribution is holding, we could still use this sort of the t-test and create this sort of a t-distribution as the t-distribution based confidence intervals for this difference, as long as we are kind of happy that this sort of a calculation, even though it is not this is not situation where the responsive variable is following the normal distribution, but we still are kind of using these sort of methods developed for the normal distribution. So in the end, we just then use the t-test. We write it as this way, as given, and the confidence interval for the difference, for the population mean difference, can be then obtained by, for example, using the or picking up the argument confined given here. So this is really what was asked to kind of return in this example, if you were forced to return something, and this is now confidence interval for 95% as usual, but we can define here, if we do the t-test, we can put here, is this the word level? I cannot now remember. 0.99%, for example, and so it's not level, it's just conf level. Conf level, like given here. Sorry, let's just write it here because I cannot remember myself how the code was working. So no, we don't see it. So okay, let's do this way. So let us do first, okay, this is the wrong one. Now yeah, and so now it worked. So we could write it in this way, and this increases the confidence interval, and that's why the lower bound for this confidence interval is even smaller number than in a case of a 95%, and upper limit is also bigger than in a case of 95%. So if we go back to the what was asked here, then we could put it in this way. So we continue next with this sort of a t-test, but we formally then says, or we consider the other functions which are related to this t-test, and more generally to the analysis of variance, and these are like a first topics to the next lecture video. But we now stop here. We have hopefully now learned few things about probability distribution, few things about how to use the sample functions, and a few things about cross-tabulation. I guess what we could take here, one thing which we haven't really used so far, is that if you look at the data set, and for some reason you want to do the cross-tabulation between, for example, let's say this retinopathy and diabetes. How many years, how long it has been since you have been diagnosed of diabetes. So since this is a numerical variable, it is impossible to create crosstab. So what we really need to do is to use this sort of a cut function. Cut diap for example in 4 categories. So this cut function will then create these sort of categories which are, I would say, pretty much equal length size, so that they would cover the whole values, and I would call this as our diabetes variable, how many years it has been from the first case of or the first situation where the diabetes was diagnosed. And now, since we have now kind of classified this our original numerical variable, we can now make the cross tabulation, or we can use this times, for example, cross tabs, and it uses the arguments like this our response variable plus this new variable. So the cross tabulation looks like this way. Sorry, I should have put it another way. No, this is the right way to do it. So I guess this diabetes seems to be having a effect on especially for the probability of this advanced level retinopathy has occurred, or blindness. But if we, for some reason we want to take this smoker here, we could then do this sort of a way, getting a three-way data set. And then there's actually this sort of a, what is the F table or what, maybe? I now forget it, this function, which kind of makes it the everything, no. Sorry, I cannot remember. It's cleaning a little bit about this X tab so that it looks more nicely on a on here, but I cannot remember exactly what was the. We could of course check the X tabs. It usually is connection. Sorry, we cannot get our internal server to work here. So let's now forget about these help sites because they are not currently working. Well, so that was the idea of using this cut function. I guess that's pretty much what I wanted to say about is that this cut function could be a useful way of turning the numerical explanatory variable, for example, as a categorical one, and then use this sort of a cross-tabulation methods to create for example, conditional relative frequencies, and that gives us the way of seeing if this X has an effect on this categorical responsive variable Y.